everyone. Please welcome Seán McCord. He's going to be speaking about Baremetal. And without further ado, take it away.
Thank you. So how many of you are actually running CoreOS Container Linux right now? Okay, so maybe half, thereabouts. How many of you are running it on Baremetal, on your own servers? Yay, all right. Good quantity. And how many of you are already network booting all of your Container Linux servers? Okay, still a fair number. Good. So that's what we're going to be talking about today. CoreOS is an excellent suite of utilities for the entire stack from the ground up, and one piece of that is getting the Baremetal servers off the ground. So I've been told that the contrast is a little low, so if you'd like to follow the slides along on your own, you can access them at this URI. So the cloud. Obviously, the cloud has been enormously beneficial for DevOps, for everything involving computers and servers. Everything from handling unpredictable growth and scaling to allowing yourself to outsource operations and expertise, distributing the initial investments of costs over time, and giving all sorts of value-added services like globally scalable databases and all of this kind of stuff. But it can be really slow. Just spending a $300 server and running an instance that'll run you at $300 on the cloud, and you'll be very disappointed at what you actually get. Correspondingly, it's really expensive. You can usually pay for hardware in about 3 months, max, for what you'd be on the cloud. And if you have specific constraints, specific needs in your deployments, well, the cloud can be a little constraining, or maybe a little maddeningly constraining. Unfortunately, getting that server off the ground involves quite a number of pieces. DHCP, TFTP, PXE, iPXE. You've got to get the OS images out there. You have to get the OS configured. You have to get the apps deployed. All of this is a lot of work. And for the handling unpredictable growth and for the outsourcing operations, that's not really all that great an operation. Luckily, with just 2 utilities, we can get all of that groundwork done for you. So DNS Mask, which is an years-old project, handles a number of things, but apropos to our purposes here, it handles DHCP, it handles a proxy DHCP server, and it handles TFTP. These are kind of archaic protocols that we really don't want to have to re-implement ourselves, and with the way we have this divvied, we can separate out usefully. CoreOS also happens to package this up nicely in a self-contained container with just a few runtime options that are all on the Matchbox site. So Matchbox itself is CoreOS's contribution to this end, and that is basically a web server that handles the iPXE, the configuration templating engine, the HTTP services, the static server assets, the TLS, the encryption, the authentication, all of the higher level tools that you need to get the server off the ground. So to cover the DNS Mask a little bit, the DHCP, everybody is more or less familiar with. It's how you get servers, or get any machine, to get an IP address, and usually the network mask, and the gateway, sometimes the DNS, and some other things. But for our purposes, we need to get the boot file reference. So this is where does your server look to get that first binary, to get that first kernel image that you can use to get off the ground, and the initial boot image. Then it serves the TFTP, which is the mechanism by which PXE uses to grab those low-level configs. So basically, you're using PXE to get the first binary from a server. Now, the problem with TFTP and PXE is that TFTP is a really restricted protocol. It's a very old, very simple, very low-level protocol. So trying to use it for any kind of dynamic structure, there's no metadata. There's no easy API service that you can just plug in and run a TFTP server. Luckily, however, we have iPXE, which is something of an extension to PXE, which for our purposes allows you to do that same thing with HTTP instead of TFTP. This allows us to provide metadata. It allows us to easily plug into, in our case, Golang, and have a full suite of operating systems and processes that you can build on top of it. And that brings us finally to Matchbox. Matchbox is basically a web server, but it's a web server specifically designed to get servers off the ground, to boot servers. So once you've finally built up from DHCP to TFTP to HTTP with the iPXE bridge, you're finally at Matchbox, and you can finally add in your TLS, your common programming interface, your HTTP distribution, and hence routing through HTTP and name-based routing instead of IP-based routing. You have your ignition templates. Does everyone know what an ignition template is? No. Okay, so very briefly, this is how you configure a container Linux machine. It's a declarative markup, JSON naturally, that allows you to define everything that happens in the OS of a container Linux machine. Extremely powerful piece of the puzzle here. It also renders these ignition templates with variable expansion. And it allows validation on the client side through hashes and, again, with TLS. So Matchbox is configured in a file and directory tree structure. By default, the base directory is varlib matchbox. And for our purposes in this talk, there are 4 primary sections of interest. Assets, which contain static assets, static binaries that can be served. Groups, which contain mappings of essentially machines to profiles. You have profiles, which map those profiles that are mapped into kernels and configs, and then the ignition templates themselves. There are a couple other sections: cloud, which is the deprecated cloud config setup, and their generic, which is a kind of an experimental open-ended templating system. So groups is the first section. It kind of is a little bit confusing because usually these don't map to groups, these map to individual machines selected by Macs. But there are 3 components to a group. One is the selector. Which machines does this group apply to? Usually, like I say, this is a MAC address or some unique identifier for a machine, but it can be any number of other selectors. The metadata, which is core to this piece, allows you to define key value pairs which will be plugged in later to the ignition templates. So in this case, we define this group as node 1, and we have the specific MAC address for node 1 here, and plug it into the config, and that's our group definition. And then we have a profile, which is pointing where do we find the config for this. That leads us to profiles, the next section. Profiles define 2 things, essentially. They define the boot parameters, which include the reference for where to find the kernel, where to find the initial RAM disk, and what kernel boot arguments to specify on the command line execution, and then pointer to the ignition template itself. So the kernel images, the initrds, as they might have been presumed to do so, are stored as assets in the assets directory. Now, the assets endpoint is actually a freeform directory structure. You can store whatever you want in the assets directory, and the Matchbox will simply expose those. But not just expose those. They'll also generate for you hashes for validation on the client side, and you can store everything from those images to TLS assets, etc., in this open-ended structure. The last part, finally, is the ignition itself. So you don't have to write formal JSON for Matchbox to work. Instead, they expose the container Linux config, I think is the name for it. But it's a YAML version of Ignition, which allows you to make it in a little more human-friendly format of YAML. This is where you place those variables that you specified in the metadata in the groups as a section to be applied within the template. So not only do you have simple variable substitution, but you actually have the entire Golang templating structure available at your whim. This includes conditionals, if-else statements. It includes iterators, like a for loop. And you can even use nested structures and functions to be expanded out inside these templates. So if you're familiar with some of the more elaborate HTML templating systems, Golang works very much the same way in their text templates that you have available for Ignition. So now that we've covered that in our whirlwind approach, let's take a look at an actual live setup of exactly these pieces in action. So we have here in this stack, if you will, a Raspberry Pi, which is our Matchbox controller, serving network DHCP and DNS and TFTP, exactly as we mentioned, and running Matchbox as well as DNS Mask on a network comprised of a 5-port switch. 2, it should have been 3, but alas, one of them bit the dust last week. Little Celeron processors, they're basically Intel NUCs. And then 1 replacement, Z8350, embedded Intel box. So all of these are running on a self-contained network that we have connected via Ethernet port from the Chrome box into this system. So we have access. This is actually running Arch rather than CoreOS because it's running on the Raspberry Pi and I didn't want to have to get the ARM builds up. But, so forgive that, please. And at least we are running everything in systemd. So we have 2 processes of interest, if I can type. We have DNS Mask, which is running and serving requests. And then we have Matchbox, which is running its process and matching ignition configurations, which, oops, that machine got turned on. Oh well, too early. I guess we'll just have it turned on anyway. So, of interest, if we shut this one down and follow the process in the boot, we'll boot one of these. Should be coming up. And there we go. So we get a DHCP request for the box that was just powered up. Of particular note, we get this vendor class in here. And is that large enough for everybody? Or do we need to increase the size? Okay, good. So this identifier is exposed and routable. So one of the key things that we miss when we're running Pixie servers on existing networks is you need to be able to classify which boxes get which piece. So while originally these were all going to be the nice same boxes, unfortunately one of these is the oddball now, the replacement box, which only supports UEFI boot, which required a completely different setup. So how do you serve both of those on the same system with the same parameters? DNS Mask exposes methods of selecting these. So if you'll recall what I just showed the tag earlier, the vendor, these are exposed here, and we set a flag if the vendor flag is Pixie Client Arch 07. Then we set the flag EFI64. This is an arbitrary label that we give, which will match the same label down here to specify which initial boot file is being used. In this case, ipixie.efi. Whereas if it's a regular old-style BIOS boot, its architecture Pixie Client 0. And in this case, we specify the UNDI-only KPXE, which is the bootstrap for Pixie to iPixie, since I left that off earlier. We have another few things just to map some DNS names, and we give static IPs to the MAC addresses. But the core of this are these DHCP boot parameters, which are telling the booting system where to find the boot pieces, the initial binaries. So that given off the ground, we have served up all of those pieces. If we look in here in the logs, which are now way beyond, we will have also seen the TFP transfer of that UNDI Pixie bootstrap. So the next piece is Matchbox. So as we can see, it's scrolling through all the various group definitions that we have, and finally matches one, group node 3. So if we take a look at varlib matchbox groups and take a look at node 3, we'll see we're matching based on just the MAC address here as the selector. We're setting a few variables since we are building essentially a 3-node etcd cluster as the demo. We define the etcd name for the node. We define what the expected initial cluster is. So in this case, we have node 1, node 2, node 3, and what their URIs are for etcd. And we specify a couple of SSH keys so that we can SSH into them. So since node 3 was just brought up, we should be able to SSH into it, and there we have it. So CoreOS running on whichever box I just turned on, this one. So etcd CTL member list is going to fail because we only have 1 out of the 3. So let's bring up one of the others. This will give us 2 out of our 3. And again, if we watch the boot up, there we go. So it has grabbed the boot.ipixie. It queried then the Pixie URL, the iPixie URL. That's these top 2 lines here. It then recalled that to get the configuration. And in a moment here, after it actually boots, it should make another call to get the ignition config after the system actually comes up. And there we go, match ignition, and the ignition config for node 2. So now, if we SSH to node 2, it's up. Up 0 minutes, and now since we have 2 out of 3 members, we fail. There we go. And should not have been up. It's not, okay. So the final one, we'll bring up the third. This one, being Intel's answer to the Raspberry Pi, takes about 90 seconds to boot as opposed to about 20 seconds. The Raspberry Pi, more like 10. So while we're waiting on that, any questions? Nope. OS installed is a common one that's actually used in a lot of the example configs. Once you get off the base level, you can start adding your own tags, and OS installed is one of them that they hand off. You can then start separating the ignition configs from that. So in one of the common idioms in the installation, you install a clean, empty CoreOS installation, then set up whatever flags you want to configure that and have it reboot and reinstall with the appropriate ignition config. So that, I believe, is how Mindblank Tectonic works. So you bring the machine up, and then after it's in the system, you can then assign that wherever it goes and set it up. And you can use that with those selectors. Right, it also can match UUIDs, it can match serial numbers that you can set on the hardware. There's a limited amount of stuff that you have available in the hardware side, in the Pixie side, and that's kind of the initial bootstrap limitation. Yes?
Well, if nothing's matched, is there a possibility for like a default option if there's no
Yes, good, thank you, I forgot to mention yet. If nothing else is matched, you can have a wildcard match that boots off. As a matter of fact, for that OS installation, for that generic base OS installation, that's frequently exactly what's used, is a wildcard match. Just don't specify a selector, and it will match anything that doesn't have another selector that's matched. So it's the most matched selector that it triggers off the group, and an empty selector, if there's no other matches, will be the final match. So that is frequently, we're going to wait forever because I just turned it off instead of on. A little more than 90 seconds. Any other questions? So while we're doing that, let's go back here and adjust so that you have this as a reference. This entire demo system, the files are all stored in this GitHub repository. It's all based on the examples in Matchbox, though. So everything in Matchbox basically maps directly out. There are a few things that are useful here, for instance, having to serve both the UEFI boot files and the base BIOS boot files. I think there were maybe a couple other interesting workarounds, but by and large, it's basically just the Matchbox example config. So definitely look there. The documentation is extensive, as with most CoreOS projects. Well documented, easy to read the code, and has lots of examples. So let's see if we're up. No, this guy is just going to be... just going to be problematic. All right, so they say it's a real computer. Let's see if it really is. If only I had IPMI on these little things, then we wouldn't have to even do this. All right, we have power. So too bad it's so small, but you can see it just triggered the iPXE. We're now booting the iPXE bootstrap. It's going to recall the DHCP, grab the kernel and the initial RAM disk, pulling those down now via HTTP. And there we are. So we've got the initial RAM disk now. So it's booting the kernel. We can't see it because it's not initialized graphics yet, but we'll see it come in shortly. There we go. So now we're into real Linux. Got systemd starting. This will take another 20 or 30 seconds because it's a really screaming fast Z83. Not quite as cheap as Raspberry Pi, but a lot slower. To be fair, it's x86, not ARM. So we're at 70 seconds, and now finally we're up. All right, so that is our 3-node etcd cluster, which is apparently misconfigured on the client side. That's because I'm not configured on the client side. I'm on the server side. But let's take a look here. Journal ctl-u etcd member. We should here, not quite up yet. It's downloading the container image. But we are up now. So etcd server is running. And established to both of those peers. So chances are we'll still not get it here. Oh, there we are. So node 1 up, node 2 up, node 3 up. So we've got a 3-node etcd cluster. Finally, with the laggard Intel Z83 just behind. So that's it. That's the demo. We have, like I say, the entire config here, and certainly any more questions I am happy to entertain. Otherwise, that is it. Yeah, absolutely. So that's the work, actually, I think, of Packet. They had a lot of the integration. I'm not demoing it here. I have no idea if these things even support it. But yes, there is integration with secure boot and even keys stored in the NVRAM. All of that's handled, I believe, by Tectonic, yes? Yeah.
So with so it's less something that is specific to Tectonic per se, but the question of integrating with secure boot and trusted execution and all that, the mechanism is that you actually become your own root of trust, unlike using the shim signing keys, which are normally used with secure boot. So you would basically countersign the CoreOS signing keys, generating those keys yourself, put them on the machines. Then what will happen is, as the bootloader comes online, it will basically validate all of our signing keys and allow that process to start. Then from there, depending on how deep you want to go with it, you can actually use similar mechanisms within Rocket to validate the keys as well. So you can actually have a signed chain of trusted execution all the way up to container runtime. So there's a bunch of documentation about it on the website. But
so all of this presumes the existence of a layer 2 network. Are there any plans that you know of to use something like Redfish to, basically what we're wanting to do is do layer 3 down to the host, and without doing DHCP forwarding and that sort of thing, is there a way we could leverage this project?
So DHCP forwarding, so proxy DHCP is a bad name. It has nothing to do with forwarding. It has nothing to do with proxying. It's just an overlay, an additional response to a DHCP offer. None of that's actually required for the booting as long as the systems themselves have some means of bootstrapping themselves. So you can decompose this process layer by layer. If you don't need DHCP, there's no reason to use DHCP. If you don't need BootP, if you don't need Pixie, there's no reason to use it. Matchbox itself operates at HTTP. That's the only interface it offers. That's the only interface it works under. As long as you can speak HTTP, Matchbox doesn't care. Not only that, it also has a gRPC interface. So if you can also interface it with custom code with a gRPC client, it works perfectly fine that way as well. So the same engine can be built regardless of your underlying layers, networking layers. What I demonstrated here, of course, yes, is built off DHCP, but nothing of Matchbox anyway requires DHCP or any layer 2, layer 3 type architecture. As long as you can speak HTTP, it doesn't really care. You could even do it over a socket if you wanted to. Sure. Anything else? All right. Well, thank you for coming.